When we increase the number of protons and neutrons, let's start again, sorry. Let me start with a new page. When we have a massive nucleus, or in other words, when we have many, okay, when we increase the number of nucleons, okay, and so on, not only this, okay, when the number of nucleons increases, there appears something interesting, which now we will try to use. Around the surface of the nucleus, okay, appears some interesting vibrations. Okay, when the number of nucleons increase, there are some interactions between the last nucleus valence. Okay, inside okay, this surface distribution of nucleons has an interesting property which is associated with the quadrupole interaction of the nucleus. This quadrupole interaction could be connected to, could be okay, comes from that the nucleons, they start there is an effective effect, or there is an interesting effect where the last nucleons after the closed shell, they have a collective behavior where now pairs of nucleons, I mean 2 protons and 2 neutrons, act like one single particle, like a boson. So, single particle with spin 0, 2 or 4, single particle with boson properties with integral spin, I mean, of or total angular momentum 0, 2 and 4, particles with this angular momentum, total angular momentum. If we have a model where we will take into account only particles with momentum angular 0, momentum angular 2 and momentum angular 4, and we take into account the interactions between them, inside the quadrupole interaction and another the linear okay, the other degrees less than the quadrupole interaction, we introduce the model that is called IBM. This is the interacting boson model. I mean, the surface effect of the nucleons which they distributing bosons with angular momentum 0, 2 and 4, when we consider this model, this model is the IBM. So, the ABM is a model of nuclear physics which nucleus pairs essentially acting on a single particle with boson properties, with integral spin 0 to 1,4. Now, the ABM1 treats both types of nucleons as like the same type, and consider only pairs of nucleons coupled to angular momentum 0 and 2. Okay, this is the general the ABM, and the ABM1 only will consider nucleons coupled to angular momentum 0 and 2. 0 will be bosons S and bosons D. This is bosons. Here the types of bosons, we don't have any kind of differences between bosons of protons or bosons of neutrons. They are almost the same. The angular momentum 0, the angular momentum is 2. Now, if we ask about bosons of protons, of bosons of neutrons, when we introduce this small difference, we call it again 2 and 2, could be 0 and 2, and 0 and 2. This is the ABM2. The ABM2 treats protons and neutrons separately, and of course the Hamiltonian should be different. So when, okay, this is the introduction of the ABM. Let me remark just to conclude that the symmetry to express the interacting boson model could be expressed by the group U6, and there are 3 types of limits of the symmetry. One of this one is U5, this is the vibrational limit, the SU3, this is for rotational or deformed nuclei, and the O6, this is the game unstable nuclei. There are 3 types of limits. Why we have different types of limits? Okay, this is something that in some papers or works that I made I explained it already, but now just I wanted to introduce this basic concept of the interacting boson model, which will be the key to develop or study and research the nuclear structure associated with the process that we were explaining before, that is associated with this, with the 0 W beta decay, with the W beta decay, and this is all the work that I wanted to explain in these basic ideas and notes. Thank you very much for your attention, and goodbye.